All right, everybody, we're going to take a look at section 3.1, which looks at extrema on an interval. That's dealing with like maxes and mins, okay? Something you may have a little bit of experience from last year, but we'll take a more in-depth look in this lesson. Now, to talk about extrema on an interval is to talk about these things called critical numbers that I have defined down at the bottom here, okay? And to talk about critical numbers is to know when a function, when its first derivative is either equal to 0 or undefined. Okay, so a critical number are x values where the first derivative is either equal to 0 or is undefined. Well, to understand where a derivative is undefined, we have to have an understanding of the sense of differentiability. Okay, so we're going to talk about differentiability of a function or relation first, and then that'll lead us into the next part, which will be extrema on the interval, your maxes and mins, okay? So I have a couple graphs here. In blue, we have the graph of function f. You can see it's kind of weird looking. There's some discontinuities. There's a vertical asymptote at the x value I'm calling e. Okay, I have some x values labeled on the x-axis there, just some arbitrary values there, a, b, c, d, e, g, h. Okay, and then up in the right I have the circle x squared plus y squared equals 1, centered at the origin radius of 1. I'm just going to use these as examples when I talk about differentiability, okay? So again, take your time, pause as you need to, and get these notes down so you understand this concept. So again, critical numbers are x values where the first derivative of our function or relation is equal to 0 or undefined, okay? There are certain times when a function or relation is not going to be differentiable. By the way, a relation is something like this circle, right? It's not a function. It fails the vertical line test, but we call these things relations. In fact, functions are relations as well. Anything that relates x and y or two variables are known as relations, okay? So, functions will pass the vertical line test, relations won't, okay? So just some terminology there. In any event, a function or relation is not going to be differentiable, also known as diffy, at x values where the function is not continuous. All right, so if you have points of discontinuity, the derivatives won't exist there. Okay, if we look up at this graph of f, okay, there are a number of points of discontinuity. Okay, this thing is not continuous at b. At c, there's a jump discontinuity, and at e, we have this vertical asymptote. Okay, so we could say that in all of these cases here, f prime of b does not exist, f prime of c does not exist, and f prime of e does not exist. Okay, does not exist where it's not continuous. Okay, why? Well, remember, a derivative is a slope, right? So if there's no slope there, right? There's no slope at that point. Okay, it doesn't even exist there. It's not continuous. Here, on this side, there's no slope. On this side, there might be. We'll talk a little bit more about left and right-handed slopes in just a moment, okay? But it's not continuous. There's no slope. And certainly at the vertical asymptote, the function doesn't even exist. So there's no slope there. So the derivatives do not exist, okay? Second condition is if the relation has a vertical tangent line, okay? So looking at this circle, okay, there are a couple of places where the tangent to this circle is vertical, right? And you should be able to look at that and see, oh, hey, over here at -1, if I were to draw the tangent line in, that's a vertical tangent line. And over here at +1, we have a vertical tangent line, okay? So the derivative doesn't exist there. Again, slope of the tangent line is the derivative, and the slope of a vertical line is undefined. Therefore, the derivative is undefined. Okay, so dy dx does not exist at plus or minus 1 here. It's actually kind of algebraically a nice thing to see here as well. If I actually use implicit differentiation on this, take a look. 2x plus 2y times dy dx would equal 0. And if I solve for dy dx, let's see, 2y dy dx, if I subtract, is equal to -2x, and if I divide both sides by 2y and simplify, we get back the negative of x over y. Okay, so there's our dy dx here. Well, let's take a look at that point. That's the point 1, 0, and over here we have the point -1, 0, right? Well, let's sub those coordinates into our derivative. dy dx at the point negative 1, 0. Well, let's see. X is negative 1, so we're going to get positive 1 over 0. And sure enough, this is undefined, right? We've got 0 in the denominator. If I evaluate this guy at the point positive 1, 0, we end up with negative 1 over 0, which again, undefined. So algebraically and through, using implicit differentiation, we can see that this is undefined at these coordinates. Graphically, it's because we have vertical tangent lines, okay? Notice there are two slopes of 0, by the way, at the top and bottom of this thing. What are these coordinates? It looks like this would be what? 0, 1 and 0, negative 1. And if we plug that into dy dx here, let's see, the negative of x over y, well, we get 0 in the numerator only, and that is 0. So sure enough, we see we get a slope of 0 here, and the same thing would happen if you plug the other coordinate in, okay? So again, but when it comes to non-differentiability, okay, something not being differentiable, vertical tangent lines, okay? Slope is undefined there. And the last one is what I call a sharp corner, where sharp corners appear on the graph. Basically what's going on is we have two different slopes coming in to the same point, okay? So like up here at the graph of f, right here at G and H, those are what I call sharp corners, okay? We more or less have two very different slopes coming into the same point. The slope coming into G from the left is some negative slope. Coming in from the right, though, it's some very different positive slope, okay? And then the same thing occurs at H. From the left, we have some positive slope. From the right, we have some negative slope. We more or less have two different slopes at these points, okay? Well, remember, again, a derivative is really what? It's a limit. And for a limit to exist, remember, the definition of derivative limit is just that. It's a limit, okay? F prime of a is equal to the limit as x approaches a of f of x minus f of a over x minus a. That was in our definition of derivative lesson, right? And for a limit to exist, what must be true? Well, the left and right limits must be equal. So basically, when we have a sharp corner and we're finding these slopes, we're finding two different slopes from left and right, okay? So more or less, what we have going on is this little section right here in blue. It says, look, f prime of a from the left does not equal f prime of a from the right. In other words, the limit as x approaches a from the left of f of x minus f of a over x minus a does not equal the limit as x approaches a from the right. And that's our definition of derivative limit, okay? So again, the gist is this, though. Look, the left and right limits don't exist, so the limit in general doesn't exist. Well, this limit represents the derivative, so I guess the derivative doesn't exist, okay? And think of a function that kind of we should be familiar with that has a sharp corner in it, okay? I'm thinking, hopefully you're thinking of the same thing as I'm drawing this. F of x equals absolute value of x, okay? The derivative does not exist at 0. We have two very different slopes coming into that point. Okay, so sharp corners. Smooth curves are fine. This is a slope of 0 at the bottom of this. We don't have a sharp corner coming in. Here the slope is kind of negative, then it's zeroing out, and now it's becoming more positive, okay? Slopes are coming together here. So regular curves and polynomials, okay, those guys are fine. Sharp corners are what we look out for, okay? So, we have to have an understanding of differentiability because we have to be able to find these critical numbers. We have to take derivatives and set them equal to 0. We're interested where slopes equal 0, but we're also interested where slopes are undefined. And so we look out for these things, okay, where the function's not continuous, the relation has vertical tangent lines, or sharp corners appear on the graph, okay? And typically endpoints of continuous intervals are not differentiable either. So like up here, f prime of a would not exist. I have a slope coming in from the right, but there's nothing coming in from the left here. Okay, so endpoints of closed intervals, not differentiable either. Okay, but let's take a look at a couple quick examples, and then we're going to start focusing more on maxes and mins, okay? So here I have a piecewise function. F of x is x squared for x values less than 1, and is the line 4 minus 3x for x values greater than or equal to 1. And let's determine this. First of all, is the function continuous at 1? And then if it is it differentiable? Okay, if it's continuous It might be differentiable. If it's not continuous, then it most certainly is not differentiable, okay? So let's check for continuity first. So let's review. To check for continuity at a point, well, is this function continuous at 1? So the first thing we want to determine, does f of 1 exist here? Okay, so let's see. Look, can we evaluate f of 1? Yeah, we would use this bottom piece. At 1, we use that. If I plug 1 in for x, 4 minus 3 is 1. Okay, so yeah, f of 1 exists. Great. Now I want to make sure, does the limit as x approach 1 of this function exist? Okay, well, since it's a piecewise and it's splitting at 1, we'll take a look at the left and right limits. Coming in from the left, I want x values a little less than 1, so I'm going to use the top piece, x squared. If I plug 1 in and square it, I'd get 1. Coming in from the right of 1, I have x values bigger than 1. I'll use the bottom piece. If I plug 1 in for x, again, I get 1. Since the left and right-handed limits are equal, the limit as x approaches 1 in general is 1 and exists. And then the kicker here is, does f of 1 equal the limit as x approaches 1 of our function? And the answer here is yes. 1 equaled 1. We got the same value back for both of these things, right? This was equal to 1. This limit was equal to 1. These things equal each other, okay? So what does that mean? It means that, yes, f is continuous at x equals 1, okay? Now we want to test for differentiability, okay? So we verified the function's continuous there, so maybe it's going to be differentiable. But now we need to actually take a look and see. So how do we do that? Well, we take the derivative of the top and bottom pieces, okay? So if f of x is that piecewise we see up there, f prime of x is going to be, all right, well, what's the derivative of the top piece? Derivative of x squared is just 2x, and that's going to be for x values less than 1. And what's the derivative of the bottom piece? Well, the derivative of that's just what? Negative 3. And now this might seem a little strange, but I'm only going to write for x values greater than 1. We don't know if it's differentiable or not, so we don't really want to define this yet. Okay, we got to figure out if it's differentiable. So to do that, we take the derivative of the top and the bottom piece, and now we look at the value of the derivative from left and right. So in other words, what's f prime as I come into 1 from the left? What's f prime as I come into 1 from the right going to be? Okay, it's kind of like what we did with our limits for the function itself. All right, well, as I come into 1 from the left, I'm going to have values less than 1. I'm going to use that top piece. And I'm coming into the left at a slope of 2. As I come into 1 from the right, that's a value bigger than 1. I'm going to use this bottom piece. And that's just negative 3. There's nowhere to plug an x, okay? You just get the constant negative 3 back. And what we see is that these values most certainly are not equal to each other, okay? So this is indicative of a sharp corner. We have two different slopes coming into this function at x equals 1. So this is not differentiable, aka diffy, at x equals 1. Okay, and actually if we look at the graph of this, do my best to kind of sketch this. It shouldn't be too bad. Look, this splits up at x equals 1. To the left, it's just the parabola x squared. So that's going to look like this. To the right, it's the line 4 minus 3x, and at 1, the y value is 1. They come together, but this is now going to have a slope of negative 3 and kind of go down like that. And sure enough, we got ourselves a sharp corner here. We've got two different slopes, slope of positive 2 coming in from that direction, slope of positive 3 as we go off in that direction. Okay, so in any event, you know, graphically you can see them pretty easily typically, but this is algebraically how we go through the process of testing. Take the derivative of top and bottom, evaluate coming in from the left and right, and see if those slopes are the same. Okay, let's try one more. Here's another piecewise. F is a cubic function, x cubed plus 8 for x values less than or equal to 2. and is 2x squared plus 4x for x values greater than 2. And notice what the question asks, is f differentiable everywhere, okay? You know, we're not going to test an infinite number of points here. There's really only one x value in question, and having said that, you can probably imagine where it's going to be. It's going to be right at 2, okay? And the reason for that is, you know, we have to have a basic understanding of polynomials. Polynomials are functions where you have like x raised to whole number powers, okay? And you studied these a lot last year in pre-calc, and polynomials are continuous everywhere, right? There's no x's in denominators, nothing like that we have to worry about, okay? So polynomials are continuous and differentiable everywhere. They're smooth flowing, they don't have sharp corners. Polynomials tend to just have like, you know, things like this going on. All right, so just something to know. Polynomials in general, continuous and differentiable everywhere they're defined, okay? So look, this cubic polynomial is certainly going to be continuous and differentiable for x values less than or equal to 2. And this quadratic, this lower piece, is going to be continuous for x values greater than 2, okay? So the question on the AP exam might ask about everywhere. It's really only going to be at the x value in question where this thing kind of splits up, all right? So just kind of watch out for wording like that. But in any event, let's again, if the question is it differentiable, we first test for continuity. If it's not continuous, it's not differentiable. If it is continuous, then we test for differentiability. So here we go. Again, to test for continuity 1, I'm going to look at, does, in this case, f of 2 exist? And it does, right? We're defined at 2. If I plug 2 into that top piece, 8 plus 8 is 16. Okay, so f of 2 exists. Now we'll test the limit from left and right. So as x comes into 2 from the left, we're on the top piece. We're going to use x cubed plus 8. Plugging in 2 again gives 16. Coming in to the right of 2, that's an x value a little bigger than 2. We're going to use the bottom piece. And let's see, if I plug 2 into that, we get 4 and 2 is 8, plus another 8 is 16. Okay, so the limit exists. The limit as x approaches 2 for this function is 16. And, you know, the big kind of kicker here is that those values were equal. F of 2 equals the limit as x approaches 2 of this function. So yes, it's continuous for those reasons. Okay, and so it may be differentiable. So let's test that now. So we're going to take the derivative of this piecewise. The top piece is just going to be what? 3x squared. And for now, I'm going to say for x values less than 2. I don't know if it's differentiable at 2 yet, so I don't want to include that equal sign. Okay. The derivative of the bottom piece is going to be what? 4x plus 4 for x values greater than 2. And so now let's look at f prime of 2 from the left and f prime of 2 from the right. From the left, I'm going to use 3x squared. It's going to be equal 12. And from the right, I'm going to use 4x plus 4, summing in 2 for x. 8 plus 4 is 12. Look at that. From left and right, the slopes are equal. We have the same slope coming in. There's not going to be a sharp corner. Okay, therefore, that's the symbol for therefore. F is differentiable everywhere. It's continuous and differentiable everywhere. Okay, we just have these two polynomials that come together. They come together at the same y value with the same slope. All right, and that's the idea with differentiability. Okay, so you'll see this concept come up as we now continue on to maxes and mins. So bear with me for just a moment. And here we go. Okay, so some notes to take. Again, pause as you need to. Go at your own pace, all right? Since a derivative is a slope, right? We've talked a lot about that. Derivative means slope, rate of change. We can make some observations here, okay? And I just have this little function off on the side here defined on the interval AB. Increasing and decreasing functions. F is said to be increasing on intervals where f prime of x is greater than or equal to 0. Okay. Increasing means from left to right the slope is positive. Okay, so here we can see our function is increasing, and over here our function is increasing. Okay. We would say basically the closed interval from A to C, the closed interval from D to B. Okay, those are the x values. From A to C, we're going up, and from C to D, we're going up. Okay, that's where the slope is positive or equal to 0. Where's the slope equal to 0? Right here and right here. We can see that in the diagram. We have slopes of 0 at C and D. Okay, but between A and C, this thing's going up, and between D and B, this thing is going up. And you might, okay, let me talk about the next part first, and then I'll make another point. Number 2, f is decreasing on intervals where the slope f prime of x is less than or equal to 0. Certainly in the diagram, we can see that here f is decreasing from left to right. Okay, on this interval right here. And that's on the closed interval from C to D. All right, well, why is it decreasing? Because slope is negative, okay? So here, f prime is positive, here f prime is negative, and over here f prime is positive again. Okay, and that's basically what these notes are saying, 1 and 2. F is increasing when f prime is greater than or equal to 0. F is decreasing where f prime is less than or equal to 0. Now, the thing you might be wondering about is, what's going on when the slope itself is 0? Well, those are called stationary points. That's number 3. Function is stationary when f prime of x exactly equals 0. Okay. At those x values, the function itself is neither increasing nor decreasing. In general, a function is just made of an infinite number of points. Points by themselves are infinitesimally small. Points themselves don't increase or decrease. When we talk about increasing or decreasing, we're talking about intervals upon which functions are increasing and decreasing. So it might seem interesting that at a single point, we can both be increasing and decreasing. Well, the point itself isn't going anywhere. Okay, the function itself isn't going up or down, but we say that that point is a member of both this increasing portion. We increase through that point, and it's also where we start the decreasing portion as well. It's a member of that interval where the function decreases. Okay, so we typically do use closed intervals for increasing and decreasing. And you don't really want to think of it as a single point that's both going up and down. It's just a member of this interval where the function itself goes up or goes down. Okay, so hopefully that's not too confusing, but I think in general the gist here where the first derivative is positive, the function goes up, that makes sense. Derivative is slope, positive slope, we're going upwards. Derivative negative, negative slope, function's going downwards. Okay, so intuitively I think that much makes perfect sense. Okay, hopefully you do as well. Okay, so again, just to recap, f is increasing where f prime is greater than or equal to 0. F is decreasing where f prime is less than or equal to 0. And we call points where f prime is equal to 0 stationary. Okay, critical numbers again are critical points. As I said earlier in the lesson, these are x values where the first derivative is 0 or is undefined. To test if a function is increasing or decreasing algebraically, what we do is we look at the critical points. We find the critical points and we test the sign of the derivative around those critical points. So I'll show you in some examples coming up. Maxes and mins. Okay, f has a relative max at x values where the first derivative changes from positive to negative. Okay, looking up here, notice right here, clearly we have what's called a relative max, our max. That's a high point. Okay, notice the derivative, positive to negative, right? Slope was positive. Now the slope is negative. Oh, that leaves us with a high point. Okay, a relative min occur where at x values where the first derivative changes from negative to positive, so the other way around. Looking at the graph, we can see pretty clearly there's a relative min, a low point right here. Well, again, look at what the derivative is doing. The derivative went from being negative to now being positive. Derivative negative, slope was negative, we're going down. Slope positive, we're going up. It leaves us at a low point. Okay, so this is called the first derivative test when we actually look at how the sign of the first derivative changes and how that gives us maxes and mins. Okay, when you're working with closed intervals, endpoints can also be relative max or mins. So in this example, I have a relative min on the left side. I have a relative max on the right side only because this is on a closed interval. Okay, and sometimes we talk about these things called absolute max or mins, and those are the highest of the high and lowest of the low. Okay, occur at the highest of the high points, the largest of the y values, and the lowest of the low points, the lowest of the y values. And typically we're dealing with closed intervals when we're dealing with absolute max and mins. If I'm looking at this again, the highest point here, not only is it a relative max, but it's also an absolute max. This guy down here, not only a relative min, but also an absolute min. Okay, the lowest of the low. Now, just to make a comment on working on closed intervals, okay, if I open this up, which I will in just a second here, okay, I'm just trying to clean this up a little bit for the next point I'm going to make for you. All right. Suppose this is open interval. Right, so these are open circles at the end now. Okay, well, these are no longer relative max mins. That's not a relative max. No way. That's not a relative min. No way. Why? Because there's nothing there. Okay, and in fact, with this graph, there would still have a relative max here, which would also be the absolute. This actually has no absolute min. This is a relative min right here, but there's no absolute min value, right? There's that y value right there that we're never going to touch. Well, what is the lowest y value we touch? I mean, if I call this the number 1, you know, how close to 1 do we get? 1.01. We can do better. We can do better than that. Right, and we can keep getting closer and closer and closer to the number 1 without ever getting there. So there's theoretically no relative min value here. Okay, so anyways, the point is this. Look, to find max and mins, we want to understand how the first derivative is changing sign. And when we're dealing with absolute max mins, we're often going to be dealing with closed intervals as a result. Okay, we have to be able to test those high and low points at the end of the interval. So let's do a couple examples here and see how this stuff works. All right, so determine where f is increasing and decreasing and find any relative extreme values. Okay, relative max and mins are also known as extreme values, sometimes called extrema. Okay, and that's just some of the terminology. So we're going to find where this thing's increasing, decreasing, and we're going to find any max or mins, okay? So first thing I notice about this is that, you know, f of x is not defined at plus or x equals plus or minus 5 here. Notice we've got a denominator. That's undefined at plus or minus 5. Those are, in fact, going to be vertical asymptotes. So those are going to be critical numbers. If the function's not continuous, we have a critical number because the derivative is not going to exist. That's what we talked about with differentiability. So this, you know, we got to look out for that. If we have a function with x's in the denominator, watch where this thing might not be defined, and those are going to be a couple of critical numbers, okay? F prime of 5 does not exist. F prime of negative 5 will not exist because the function's not continuous there. Okay. Now, to find where the function's derivative is equal to 0, we got to look at the derivative. All right, well, I'm going to use the quotient rule here. Derivative of the top times the bottom minus derivative of the bottom times the top all over bottom quantity squared. And let's see if we clean this up. We're looking at 2x cubed minus 50x minus 2x cubed over the quantity squared, which is negative 50x over the quantity squared. Okay, so we can see where that equals 0 by setting the numerator equal to 0. And solving for x, we just get x equals 0. Again, we could use this to see where this is undefined. Notice that this is also not defined at plus or minus 5. If the original function isn't defined there, the first derivative certainly isn't going to be defined there either. So if we didn't really notice that about the function to begin with, we got to remember, hey, look, this is the derivative. The derivative is 0. When the top is 0, it's undefined when the bottom is 0. Okay, so again, plus or minus 5 critical points. If you're not dealing with a rational function with x's in the denominator, you really don't have to worry too much about that. Okay, but in any event, we got 3 critical points here. Critical numbers are x equals plus and minus 5 and 0. Okay, so those are the critical numbers. And so now what we're going to do is we're going to do what's called the first derivative test around these points to determine where the function's increasing and decreasing and where we might have any max or mins. Okay, so I'm going to make a number line, and I'm going to put my critical numbers on there from left to right. These correspond to x values on the bottom. Up top, I have the f prime symbol, and f prime of negative 5 was undefined, so I put a u there to indicate it was undefined. F prime of 0 was 0, so I put a 0 up top there, and f prime of 5 was undefined, again, at 5. And now what I want to do is I want to look at the sign of f prime in these regions. We're going to test the sign of f prime in the 4 regions we have, okay? So, for example, over here, I want to take any x value less than negative 5. In here, I'm going to take an x value in between negative 5 and 0, say like negative 1. Here, I'm going to take an x value in between, and over here, I'll take an x value in between. And I just want to see if f prime comes back positive or negative in these regions. Because if it's positive, I know the function is increasing in those regions. And if it's negative, I know it's decreasing. Okay, and we'll see how all this comes together very soon. Okay, so look, here's our f prime as simplified as we got it. Don't work too hard to test the sign of this thing. What do you notice about the denominator? The whole denominator is what? Squared, right? What sign is the denominator going to be if the whole thing is squared? As long as it's not equal to 0, right, it's always going to be positive. So I know the denominator of this thing is always going to be positive. So I'm not going to work too hard to punch numbers into that, okay? So basically what I'm going to do is I'm going to look at the sign of the numerator. Whatever the sign of the numerator is, I'll have either a positive over a positive or I'll have a negative over a positive. And it'll be pretty easy to determine based on what x is, what that's going to be. So let's start at x equals negative 6, some number to the left of negative 5. Well, I have a negative 50 times a negative 6 in my numerator, right? I'd have a negative 50 times a negative 6 over my positive. Well, that looks like it's going to come back up positive. So f prime is positive for x values less than negative 5. And what does that tell us about the function in general? Well, it means the function is increasing. So I draw a little line going up and to the right in my diagram to indicate the function is increasing. Okay, now I'm going to move on to the next region. Okay, say I take x equals negative 1 and I plug it into the first derivative. I've got negative 50 times negative 1 in the numerator, again over a positive denominator. Well, that came back positive again. So my function is still increasing. Okay, let's draw a line up and to the right. Now I'm going to take a number like positive 1. Negative 50 in the numerator times positive 1 over a positive denominator. Well, that looks like I have a negative over a positive. That whole thing came back negative. And if the first derivative is negative, that means the function is now decreasing. And if I take a number like positive 6 and plug it in for x, I have negative 50 times positive 6 over a positive denominator. Again, that's going to come back negative. And so my function is still decreasing. And so now I have basically everything I need right in this table, okay? The question was to say, well, look, find where the function is increasing and decreasing. Okay, well, f is increasing, it looks like, from negative infinity up to negative 5. And then again, from negative 5 up to and including 0. Okay, nothing at negative 5 because the original function's undefined there. There's a vertical asymptote. That's why negative 5 was left out. Negative infinity is left out on this open interval because you can never get there. But at 0 is where the function stops increasing. F is decreasing. Well, when the derivative is negative, that was from 0 to 5. we include 0 but not 5 because the function's not defined at 5, excuse me. And then again, it's decreasing from 5 forever. So from 5 up to infinity. That's where the function's increasing and decreasing. In terms of relative max-mins, we actually only have one relative max. There's one spot where the derivative changed from positive to negative. And we can see it in the diagram. We were going up. Now we're coming back down. We have ourselves a relative max at x equals 0. And typically on the AP exam, you're asked to justify your answers, okay? So if you're asked to say why do we have this relative max? Well, it's because f prime of x changed from positive to negative. Okay, so you want to include your reasoning typically. All right, and why are these? F is increasing because f prime of x is greater than or equal to 0. Here, because f prime of x, f is decreasing because f prime of x is less than or equal to 0. Okay, so again, here we have this rational function, quotient rule to take the derivative, but I like this example because it not only gets you thinking about where the derivative is 0, but also where the thing is undefined. Okay, and this is how we test signs and make sense of the sign of the derivative on top to what the function is doing going up or down on the bottom. Okay. Take a look at another example. Here we have a polynomial now, no rational functions, so I'm not really worried about x, this thing being undefined, okay? So we have this function, 3x to the fourth minus 4x cubed minus 12x squared plus 3 on the closed interval -2 to 3. Find the absolute max and min values of this function, okay? So we want the highest of the high values and the lowest of the low values. And we want the absolute max and min values. Okay, the implication are the y values, okay? Okay, it doesn't say determine at what x values the max and min occur. It says find the highest and lowest values here, okay? So, we're thinking up and down. Those are the y values. Okay, so anytime a question asks about max min, hey, let's take a look at the derivative. So f prime of x here, pretty easy, 12x cubed minus 12x squared minus 24x, okay? Again, nothing that indicates this is undefined anywhere, so we don't really have to worry about that. Let's just set it equal to 0. And we can certainly factor a 12x out of this. And I believe we can refactor the trinomial. Okay, and so it looks like this is going to have 3 zeros. And again, let's keep in mind we're on the interval -2, 3, but let's check out what the zeros are. It looks like x equals 0, x equals +2, x equals -1 are our critical numbers, or the critical points you might call them. And all of those occur within the closed interval, okay? So we're going to make a number line, and we're going to test the sign of the derivative around these values. Now, one thing I want to keep in mind is that I'm on the closed interval from -2 to 3, and I'm going to indicate that on my number line here. Okay, from left to right, the critical numbers -1, 0, and 2. So again, the bottom are x values. The top is what's going on with f prime. At -1, f prime equals 0. At 0, f prime is 0. And at x equals 2, f prime is 0. Okay, so that's my labeling. X values on the bottom corresponding to what's going on with f prime up top. All right, now, testing the signs should be pretty easy if we use the factored form of the derivative here. So let me just rewrite this here. Okay, and I'm going to take x values in each of these regions again. So here I'll take like -1.5. I'll test it like -0.5. Maybe +1, and then maybe like 2.5. Actually, I can use the endpoints of the interval. There's nothing wrong with that. That's easier than those fractions. So we can use the endpoints of the interval. There's nothing wrong with that. Okay, so I'm going to pick some convenient values to test the sign of f prime. At -2, let's see, 12 times -2 is negative. -2 minus 2 is negative. And -2 plus 1 is negative. And the product of three negatives is negative. So our function is decreasing on that interval. At x equals -1/2, 12 times negative anything is negative. -1/2 minus 2 is negative. -1/2 plus 1 is positive, though. So this product is going to come back positive. So the function's derivative is positive on that interval. We're now increasing. And what did we just find? We found ourselves a relative min. We went from decreasing to increasing. We see that low point. Okay, let's test at x equals 1. 12 times 1 is positive. 1 minus 2 is negative. 1 plus 1 is positive. That product comes back negative. We're decreasing on this interval. And look, we found a high point at 0. And finally, let's test at 3 itself. At x equals 3. 12 times 3 positive. 3 minus 2 is positive. And 3 plus 1 is positive. So that product certainly comes back positive. And now we're increasing on that last interval. And we found another relative min. Okay? And guess what, folks? We have two more relative maxes here because we're on a closed interval. This function is increasing from 2 to 3. This is ending at a high point. You got to watch that, okay? That's included in the interval. And at -2, we actually started at a high point. We started up and we're coming down. So this is also a relative max. Okay, so watch the endpoints of the intervals. When you're dealing with closed intervals, you have to keep those endpoints in mind, okay? So we actually have a lot of critical points here. We've got 2 mins and we've got 3 maxes. So let's take a look at them separately. We got mins, we got maxes. And so I'm going to have to see, what's the lowest of the low. So I got a min at -1 and I got a min at x equals 2. So I'm actually going to evaluate the function at -1 and I'm going to evaluate the function at 2. And I'm going to see which one comes back lower, okay? So basically, remember, go back to the original function to do this, okay? Those are where the first derivative is 0, okay, or something. But to get the actual y values, we got to go back to the original function, okay? And don't work too hard to do that. Feel free to use a calculator by all means. That's certainly what I'm about to do here. So give me just a sec. Okay, so f of -1, I am getting -2. When I plug -1 into the original function, I'm getting -2. And when I plug 2 into the original function, I actually get -29. So which is lower? Well, clearly -29 is lower. So the absolute min value is -29. That's the lowest of the low values here. For the maxes, we've got 3. We've got at the endpoint of -2 a high point. At 0, we're at a high point, and at +3, we're at a high point. So again, I can plug each of those back into this original function and get the y values. In doing so, we're up at 35 when I plug -2 in. We're at 3 when I plug 0 in. That should be fairly easy to see. And when I plug 3 in, we're up at 30. So the highest of the high is at 35. So our absolute max value is 35, and we just found the absolute max and mins. Okay, so again, the point of this is to watch the endpoints of the interval, okay? Here's another example. F of x is x cubed minus ax squared plus b. F has a min at the point 4, -17. Find the values of a and b. All right. So at this point, we know the function has a min. Based on that, we're looking for these coefficients, okay? Number a in front of x squared and that number b, okay? Well, one piece of information we have is this, right? If I plug 4 in for x, the y value is going to be 17, right? Or -17. So using this original function, I can do that. F of x is the y value, so I know if plug, okay, negative 17 is the result of plugging 4 in for x. Okay, and I can clean this up a little bit if I want here. Let's see, that becomes 64 minus 16a plus b. I can move the 64 around if I want, but this in and of itself is not enough to solve for a or b. Okay, we need to know the value of one of those to get the value of the other. So that's one thing we can do, but it only leads us so far. So the next is to really understand, well, what does it mean if this function has a minimum? Well, since this is a polynomial, it meant that f prime must have changed from negative to positive at that x value of 4. And what does it mean if this polynomial changed signs from negative to positive? Well, I guess it means the first derivative must have equaled 0 at 4. Okay? If we know the location of a max or min of a polynomial, we know the derivative must have equaled 0. Okay? And that was what was going on in these examples here. Setting the derivative equal to 0 and finding those max and mins at those sign changes. Okay? So again, here you got to understand the concept. If we have a min at this x value of 4, it means the derivative equals 0 at 4. So what are we going to do? We're going to take the derivative of this function, which would be what? 3x squared minus 2ax to the first when we take the derivative of this guy. Okay? Plugging 4 in for x, we know the derivative equals 0. So I'm going to make the derivative 0 when I plug 4 in for x. All right, and now we can solve for a. Once we have a, we can come back over here and solve for b. All right, so over here, setting the derivative equal to 0, we plugged 4 in for our x value, and we're going to get what here? 48 minus 8a is equal to 0. So I'll add the 8a over, and we get a nice value back for a here. It looks like a is 6. Okay, so now that we know a is 6, we can come back and solve for b in this equation. And let's see, negative 17 is 64 minus 96 plus b. 64 minus 96, I want to say is negative 32, but I'll verify. Yes. And adding the 32 over, and we're looking at what? 15. Okay, so we did it. We found the values of a and b. At the point 4, negative 17, we're able to get so far. Okay, then we had to make the other connection that since we had a min or even a max, it really wouldn't have mattered which one it was, but since we have a critical point, we set the derivative equal to 0, so we took the derivative, we set the derivative equal to 0, and plugged in that given x value. Okay, so try to process that and reach out if you have questions. Here's now one with a piecewise, okay? F of x is the piecewise, x squared plus 1 for x values less than or equal to 2, and is the line negative 2x plus 8 for x values greater than 2. Where is this function increasing and decreasing, and find the relative extrema. Okay, so again, to the left of 2, this function is a continuous indifferentiable polynomial. It's just a quadratic. To the right, it's a continuous indifferentiable polynomial line. Okay, at 2, we really should be seeing if this thing is differentiable or not, because that could be a critical point. Okay, so let's go ahead and take the derivative of this thing. All right. Well, I'm going to test for continuity, I guess, first. Let's see. Does f of 2 exist? Yes, we can see that it does. And when I plug 2 in, 2 squared is 4 plus 1 is 5. The limit as x approaches 2 from the left is going to be using that piece as well. The limit as x approaches 2 from the right would use the bottom piece. Negative 4 plus 8 is 4, so the limit does not exist. So this is not continuous at 2. So we have a critical point at x equals 2 because f prime of 2 does not exist. Why? Because it's not continuous at 2. Again, I kind of just know when I'm looking at these piecewise, kind of train myself to think about that test for continuity. Okay, so all right, we do have a critical point at 2. The derivative doesn't exist at 2. Great. Let's go ahead and take the derivative of this thing, though. The derivative of the top piece is what? 2x for x values less than 2. The derivative of the bottom piece is just negative 2 for x values greater than 2. Now, look, another way to see that this is not differentiable at 2 is to test f prime from the left and right. If I come into 2 from the left, I use 2 times 2, which is 4. If I come into 2 from the right, it's just negative 2. The slope is negative 2. They don't equal each other. Okay, so again, f prime of 2 does not exist. So if you didn't catch it up here, that's how you catch it. But you got to think about testing. Okay, you got to think about non-differentiability. Okay, now we also have to consider where these pieces themselves could equal 0. So look at this. For x less than 2, that's the top piece. Let's set this equal to 0. Okay, so look, divide and you get x equals 0. X is 0. Is that less than 2? Yes, it is. So we have a critical point at x equals 0. So critical point we set at 2, but also at 0. For the other piece, when x is greater than 2, does negative 2 itself ever equal 0? No. There's no x to solve for. That piece never equals 0, so there's no more critical points. So this function has 2 critical points. At 0, the slope is 0. At 2, the derivative is undefined. Okay, so let's take a look at our number line here. And from left to right, our critical points. We determined the derivative was 0 at 0 and is undefined at 2. And let's see if we start testing signs of this thing. Okay, for x values less than 0, let's use x equals negative 1. I'm going to use x equals 1, and I'm going to use x equals 3 to test. So let's look at f prime. So again, f prime's a piecewise. F prime of negative 1. Well, that's less than 2, so I have to use the top piece. So 2 times negative 1 is negative 2. That's negative. That's all I really care about. F prime is negative. The function's decreasing. At x equals 1, well, that's also smaller than 2, so I'm still using the top piece. 2 times 1 comes back positive. So our function's increasing, and it looks like at 0 we found a relative min. Okay? And our function is continuous at 0, so that's fine and good. Now, the derivative is undefined at 2, so we're testing around it. Let's take a look at f prime of 3. Got to be careful. Now we're dealing with an x value greater than 2, so we're using that. And that's just negative 2. F prime of any number bigger than 2 is negative 2, so that's certainly negative. And we're decreasing again. Okay, so we can say where f is increasing and decreasing. F is decreasing from negative infinity up to and including 0, and again from open to infinity, because f prime of x is less than or equal to 0 there. F is increasing closed 0 to open to, because f prime of x is greater than or equal to 0 there, right? Where it's undefined, nothing going on. Okay, and we have a relative min at x equals 0. Okay, that's supposed to say at x equals 0, relative min at x equals 0, because f prime changes negative to positive, and we looks like we could have a relative max at 2, even though the derivative is undefined there. And even though the function's not continuous there, the function is defined at 2. And the notes say if the derivative changes from positive to negative and the function is defined, we could have a relative max. So let's take a look at what this is. Relative max at x equals 2, because f prime changes positive to negative. Okay, this graph is for the last example coming up in a moment, so try to ignore that. All right. But let's take a look at this thing. So look, I'm going to graph this piecewise function real quick. And let's try to make sense how we have a relative max at this one point. All right. So look, this thing splits up at x equals 2. To the left of it, it's the parabola x squared plus 1. So that would just be a parabola shifted up 1 unit. And at 2, we have the y value of 5. And to the right of 2, we have the line negative 2x plus 8. Now, when we plug 2 in it, we had a y value of 4, and it's not defined there. And this has a slope of negative 2, so that's going down and to the right. So sure enough, you know, there's no slope at 2. Derivative doesn't exist because it was undefined. We got that the first derivative equaled 0 at 0. Look at that. The slope of 0 is 0. Right? At 0, the slope is 0. That was this that we solved for. That was that on our number line. We said we had a min there, do we? Yes, we do. Look at that relative min. We said the function was decreasing and then increasing. It was. We said the slope was undefined at 2. It is because the function's not continuous. We said we had a relative max at 5 because the derivative changes from positive to negative. It does, and the function is defined there. Notice we have this relative high point. Okay, so piecewise tend to be, you know, a little more thought-provoking with things we need to look at. Got to be careful with those. Polynomials, usually pretty easy to deal with. Okay, and you'll see a number of those. Rational functions, again, watch out for the quotient rule. Watch out for where the denominator and numerator is 0. Okay, and one final graphical set of examples here. Here's the graph of some function f prime. Okay, let me get rid of these from the last example just to clean this up a little bit. And these are pretty popular on the AP exam where they give you graphs and they ask you to answer with justification. So based on the graph of f prime above, we should be able to answer these questions, okay? On what intervals is f increasing? Well, f increases when the first derivative is positive, okay? When f prime is positive, greater than or equal to 0, I should say. So that's your justification. I tend to start with the justification. Okay, so when this is first derivative is positive. Well, when is the graph of the first derivative positive? It's when the graph itself is above the x-axis. The graph is positive in these regions, greater than or equal to 0 in these regions. So that's going to be from negative infinity up to and including negative 2. And then again from 0 to infinity, really. We can go 0 to 4 like this. And then we can include 4 to infinity, but we may just go right from 0 to infinity, okay, because it's closed intervals. All right. When is f decreasing? Well, the function decreases when the first derivative is less than or equal to 0. If you're looking at the graph of the first derivative, when is a graph less than or equal to 0? When it lies below the x-axis. So that's going to be on the closed interval negative 2, 0 here. Okay. Now, some students have a hard time looking at the graphs. Some students prefer this algebraic approach where you find the zeros, you make the number line, and you test. Look, it's very easy to take a graph of f prime and turn it into the number line. So if you want to do that, it works like this. Look, we're going to have x values here, f prime above. We want to find the critical points. That's where the first derivative is 0 or undefined. Well, this graph is never undefined, but the graph is 0 here and here. Okay, when it touches the x-axis, that's when it equals 0. The y value of that graph is 0. So the critical points are at negative 2 and 4, and I missed one. Where's the other one? Hopefully you see it at 0 there, right? That crosses at 0 too. Now I want to test the sign of f prime. When the graph is above the axis, it's positive. That's to the left of negative 2, from 0 to 4, and then from 4 to infinity. When the graph lies below, that's when the thing is negative. That's only on the interval from negative 2 to 0. And now we can sketch, increasing, decreasing, increasing, and still increasing. Okay? And we can see those intervals now. Increasing, negative infinity, negative 2, increasing from 0 on, decreasing from negative 2 to 0.
We can also see the maxes and mins that way, okay? So if it helps, take the graph, turn it into the number line. At what values of x is f stationary? That's exactly when f prime of x equals 0. Those were the x values of -2, 0, and 4. Where does f obtain any relative max? That's when f prime of x changes from positive to negative. Okay. Again, you can see it in the number line. That's at -2. That's the only one. Let's look at the graph, though, so you know what to look for if you're solely or just looking at the graph here, okay? What does it look like to change from positive to negative? From above to below the axis. That's what that looks like in -2. Okay, it's coming from above to below the axis there. Okay. And where does f obtain any relative minimum values? That's when the first derivative changes from negative to positive. And this is the way you want to do your justification. You want to avoid saying things like, you were working on the graph, right? So don't say things like, oh, when it changes from positive to negative, when it changes from negative to positive. You want to avoid words like that. On the AP exam, you won't get credit for it, okay? Nor on my exams. You got to be very specific, okay? It's when f prime changes from positive to negative, negative to positive, okay? So again, here in the number line, we can see it, relative min at 0. There was our low point. Sure enough, derivative went from negative to positive. In terms of the graph, it's right here, okay? The graph goes from below the axis to above the axis. That's what it means to change from negative to positive. And again, that was at x equals 0. And while x equals 4 is a critical point, okay, the derivative is 0, it's not a max or min here. Okay, it just happens to have a slope of 0 there, but the sign change never occurred. The derivative is positive and positive, which is why the function continues increasing through the x value of 4. Okay, but all sorts of different ways you're going to be asked about maxes and mins. So take some time to digest all this. Make sure you got all these different testing procedures down and work on your algebra. And if all else fails,